you can sometimes take a function, and when you differentiate it a lot, you see some sort of pattern. So for example, you need to be able to write down a formula for the pattern. So for example, we can start with sine. Okay, if you differentiate this, let's just do, what symbol should we use? D by dx. Okay, if you differentiate it once, you get cos. If you differentiate this, you get minus sine. Right, so sine differentiated is cos, cos differentiated is minus sine. Minus sine differentiated is minus cos. Minus cos differentiated is sine again. Okay, look, you're back to where you started. So it's a 1, 2, 3, 4 cycle, kind of. Right, you go through 1, 2, 3, 4 steps, should I say. 1, 2, 3, then you're back. Yeah, we count 1, 2, 3, 4, and then you're back to where you started. I could even write it like this. Okay? Do you see the pattern?
Mm-hmm.
Well, I mean, not a pattern, but do you see that there is a pattern? Let's put it like that first. Okay. So now we need to think of a clever way to write the pattern. There's quite a few clever ways to write the pattern. But first of all, you can see and go, okay, one thing I can notice is, if I ask you, this is what they mean by higher order derivative. They could ask you d, that's not a good one, that's the bad one. If they say to you, consider d by dn, turns out that was the big one. Consider d by dx of sine of x. Okay, that's pretty straightforward, it's just cos. But now you see what you do, you put an n up here and an n down there. That means do the derivative n times.
Okay.
Yeah, so if it's 3, then it's d3 by dx cubed. I'm not supposed to say cubed, to say 3. So, d3 by dx3. That means differentiate with respect to x 3 times. That's what that symbol means. They ask you, write out a formula for this in terms of n. That was a general formula for what this is in terms of n. Now you could do it in a kind of brute force way. This is the ugly brute force way to do it. Have you ever seen a function defined like this? It's something if this, something if this. You know these functions, piecewise. It's called, they define piecewise. So 0 if n equals 1, 1 if, you know what I'm talking about. This is obviously not the answer, but it's this. It must be in terms of n, not x. You're going to leave the x here. The x is still going to be here, because the x is there, the function is to do with x. Your formula must be to do with n. So what you could say is, how about this? You could say something like, so let's check. This is when n is 0, this is when n is 1, this is when n is 2, this is when n is 3. So when n is 0, you differentiate. And then after that, you go back to 0. So then you could say something like, you have all your cases. It could be n. Do you know what n mod 4 means?
Yes.
You do know what it means from computer science. So n mod 4 basically means, okay, you have div and mod. Do you still have div and mod?
Yes.
Hey, you do. So n mod 4 basically means the remainder after you've divided by 4. So something could be, any natural number mod 4 would either be 0 mod 4, well, it's something like this. If n equals 0 mod 4. That's an option. A natural number would be 0 mod 4. It could also be 1 mod 4, right? It could be 2 mod 4, or it could be 3 mod 4. You see, it can't be 4 mod 4. If the remainder was 4, you divide by 4, well then the remainder is actually just 0. You have an extra factor of 4. Okay? So these are all your scenarios. And now you just write out all the options, right? For here it's sine of x, here it's cos of x. Do you see how this works?
Yeah.
Every time I get back to 0 mod 4, well, I go back to sine, and then minus sine and minus cos. And yes, hello video people, I hope you can see this. That's This is true, but it's a very like brutish way of doing it. It's almost like computer science. You've literally done case by case by case by case, and it doesn't look nice. For sine and cos, there's a very nice way of doing this one actually. It's good I'm showing you because you won't think of it yourself. It's tough to think of this without someone showing you on a picture. Okay, for starters, let's think about sine of x. What does it look like? It looks like this. What are these values? That's 90. That's 180. Right? That's minus 90. That's minus 180. Okay, you're happy with the sine graph?
Mm-hmm.
I think that's what a sine graph looks like. Yeah. Okay. Now we do cos. What does cos look like? There, it's at max of 80. There, it's 0. Here it down at 90. It hits its minimum at minus 80. Where this is a max, it comes back and hits 0. Okay? That's cos. That's sine. So let's just remember that this is the 0th derivative of the thing we started with.
Yes.
Meaning you haven't derived it at all. This is the first derivative. You've derived it once. Minus sine. What does minus sine look like? Okay, well now it's easy, right? We can take the sign we've got and just flip it around. Okay? And maybe I should. I've had a different color. Let's just see where. Okay, I'll do this so we can all see what it is. I'm just making it squiggly so that we can easily compare. What's this one? This one is the. Did I do that right? I think I did. That's also minus cos, but we could write it as the second derivative. It's the second derivative of what I've got. No, it's minus. Not minus cos. Okay. It should be fine. I think there's sine there. Everything right? Yes. Okay, and here's the part where you notice, this is where you kind of look at this picture and go, actually, hang on. Everything here is the same shape. It's just getting shifted all the time. So let's check. What's my first shift? I started with the sine, and then it looks like I shifted 90 degrees to the left.
Yes.
To get this derivative. That's this one. Now let's take this one. What did I do to get to the next derivative? I shifted 90 degrees to the left again. That's the key observation. And if you want to really check, you do minus cos. This one's cos, so minus cos would be like that. And now, maybe let's do some things we can really tell. And now what's that one? How do I get to that one from this one? Shift to the left by 90. Can you see, starting at the 0th derivative, you shift by left to 90 to get to the first derivative, then you shift by left to 90 to get to the second. You keep shifting by left to 90 to get this. So a prettier way to write this is you say it's just sine of x shifted to the left. Remember, you put a plus if it's inside. Do you remember how to shift things? Or you learned yet in core maths how to shift functions left and right. The way to shift a function left, if you have a function f of x, the way to shift it left is to change it into f of x plus the shift, however much you want to shift it by. If you change f of x into f of x plus s, this will take f of x and shift it to the left by s. Okay, so what do? Plus 90 degrees right, but n times, however many times you differentiate it. There we go. That works. And don't you agree this is a much prettier version of the formula than that other big brute force thing we had? And we can kind of see if it works. Let's check. If n is 0, you get sine of x. True. If n is 1, you get sine of x plus 90. Well, we can kind of see in the picture. Sine of x plus 90 is the same as sine of minus x minus 90, which is the same as, sine of 180 minus x minus 90, which is 90 minus x, which is cos of x. Okay, then next is sine x plus 180. Sine x plus 180 is minus sine of x. Yeah, you gotta think of the things in your head. But sine of 180 plus, think of it this way. I hardly ever remember those identities. I kind of just remember 2 and then I always fiddle with it to make it equal to the one I want. But sine of 180 plus x, well, we can say this is, we can make it a minus, if we make it a minus, that's fine. Right, you know you're allowed to do that. because minus sine of x is minus x, so we can put a minus there. Then what can we do here? We're allowed to add 360, so let's add 360 minus 180 minus x. You can add as many 360s to sines and coses as you want. 360 minus 180 is 180, and then 180 sine of 180 minus x, I just know that's just sine of x. So it becomes minus sine. Okay, it works. Anyway, this is the wonderful, I don't know what you call it, an identity or something. Formula is called the formula. That's the formula. Wonderful, beautiful. Hard to see if you've never seen it before. Certainly, if you never thought to look at how the graph is actually just shifting 90 degrees every time, you wouldn't have thought of it. But it is the best way to write a higher order derivative. And do you see why it's called a higher order derivative? Because you can do as many differentiations as you want. You'll never run into problems. So this is what the textbook means when they say higher order derivatives. They don't mean f double dash. I mean, that's like that's the second order. They mean higher order, like 100. You do it 100 times. That's what they mean when they say higher order derivatives. Cool? Okay.